Okay, in this video with rules of inference, we're going to extend things beyond just propositions and look at predicates and quantifiers. Now over here you can see we have a new set of rules of inference to add to our existing rules. All the rules like modus ponens and modus tollens and all the ones with implications and ands still work, but now we also have to deal with quantification. For example, this first rule over here says for all x, p of x is the premise. Well, if we know that a predicate p of x is true for every x, then it certainly must be true for any particular c we pick. This is called instantiation because we're taking something that's general and applies to all x's and making it apply to one specific instance of it. We can also do the flip side of that. If we know that p of c is true for any arbitrary c, then it must be true for all x. Now you do have to be a little bit careful with the existence quantifiers. To say that there exists x, p of x is true, means that p of c must be true for some c, but not any particular c. Okay, so let's take a look at how we would do an example here. We have some premises over here. Linda, a student in this class, owns a red convertible. Everyone who owns a red convertible has gotten at least one speeding ticket. The conclusion is, therefore, someone in this class has gotten a speeding ticket. As soon as you see words like everyone and someone, you should expect to have to use quantification. So we're going to have to translate things, but we've got a few extra things to do here. First, we're going to have to come up with predicates. We can see that we're going to need to be a student in this class, we're going to need to own a red convertible, and we're going to need to deal with getting at least one speeding ticket. So we'll make predicates. We'll let s of x mean that x is a student in this class. We will let O of x mean x owns a red convertible. These names are arbitrary. And then we'll do t of x. We can't use s for speeding because we already have s taken for student. So we'll use t of x, that x has gotten a speeding ticket. Okay. Now that we have our predicates, it's time to try to translate our premises. The first sentence says, Linda, a student in this class, owns a red convertible. So we should say s of Linda and O of Linda. Okay? So Linda is the variable or instance for our predicates s and o. Now the second predicate over here that starts with a premise over here that says everyone who owns a red convertible has gotten at least one speeding ticket would be translated as such. For all x, O of x implies t of x. Sometimes these are a little bit trickier to see. You don't see the if-then, but you're saying here, for everybody, if you own a red convertible, then you've gotten at least one speeding ticket. Okay, let's give ourselves a little bit more room here to work. Okay. So we have our premises set up right here, and we have to come up with a conclusion that someone in this class has gotten a speeding ticket. So if we put together s of Linda and O of Linda together with for all x, O of x implies t of x, well, if we know that O of x implies t of x for all x, then it certainly must work for Linda. So O of Linda must imply t of Linda. Right. And we know that we already have O of Linda. Right? And if you put those two rules together, you can therefore conclude t of Linda. Okay? We also already know, as our first premise says, that s of Linda. So we can put together t of Linda and s of Linda. Now, going back to our premises up here, if p of c is true for some element c, then there must exist a p of x for which it's true. So if we already know that this is true for Linda, then we can generalize that to say there exists x, t of x, and s of x, which is what our conclusion says. Let's go back up and look at that. Our conclusion said, therefore, someone in this class has gotten a speeding ticket. And if you look at our conclusion over here, t of x and s of x, meaning in this class, x is in this class and has gotten a speeding ticket.